Soil crusting is the formation of a thin, compacted surface layer with a higher bulk density than the soil immediately beneath it. This slide visually illustrates various forms and consequences of soil crusting in different agricultural settings. The mechanism for soil crusting involves the beating action of raindrops or slaking action of irrigation water, leading to the dispersion of finer particles. The dispersed material clogs soil pores. Coarse particles settle first, while fine clay particles remain suspended, eventually forming a dense surface crust upon drying, which reduces water infiltration and gas exchange. Soil crusts are characterized by high penetration resistance, high bulk density, and low porosity. Their thickness can vary from millimeters to a few centimeters, depending on the clay and silt content. Crusting is generally less common in sands, but is more susceptible in silty clay loam alluvial soils. Soils with less than 1% organic matter are also more prone to crusting. Susceptible soils typically have low organic matter, high silt content, and a high exchangeable sodium percentage. The strength of a soil crust increases linearly during the first few days of formation. Thickness increases with clay content and depends on the size of raindrops. Hardness increases with silica, oxides, hydroxides of Allan Fay, calcium carbonate, and silt content. Adverse effects of crusting include reduced germination and emergence of seedlings, decreased water infiltration, increased runoff losses, and slowed or ceased gas exchange between the soil and atmosphere. There are three main types of soil crusts: structural crusts, erosion or depositional crusts, and cryptogamic crusts. Structural crusts include slaking crusts, which are thin and dense, and infiltrating crusts, found in medium textured soils, resulting in clear textural separation. Other structural crusts are coalescing crusts, formed in wet soils where surface porosity is low, and sieving crusts formed on sandy soils, creating two contrasting layers. Erosional crusts form when the loose surface layer is removed by overland flow, leaving fine particles exposed. Depositional crusts form after surface sealing and concentration of detached particles or microdepositions in furrows. Cryptogamic crusts are surface crusts made of algae, fungi, lichens, mosses, and bacteria. They are also known as microphytic crusts. The strength of soil crusts can be evaluated using three techniques: the penetrometer, the balloon pressure technique, and the modulus of rupture test. The penetrometer measures penetration resistance in $text kilogram/text cm squared dollar by steadily pushing a pocket penetrometer into the soil. The balloon pressure technique involves burying a balloon and measuring the pressure required to inflate it to the point where it ruptures the soil surface. The modulus of rupture test measures the force required to break a rectangular soil briquette using the formula S equals $3 FL dollar divided by $2 BD caret $2. In sandy loam soils of arid and semi-arid regions, soil crust can limit the emergence of crops like pearl millet, cotton, and mung bean, but not cluster bean and maize. The maximum crust strength in these soils is about $3.50 text kilogram/text cm caret $2. Crops like maize and cluster bean have higher emergence forces compared to pearl millet, cotton, and mung bean, making them less affected by crusting. Managing soil crusting includes vegetative mulching, ridge sowing for better emergence, immediate scrapping of the crust with a tined hoe, adding organic matter, and light irrigation after crust formation. And that's the end. Thanks for watching the video. For more videos, subscribe to my channel, JRF Soil Coach, and don't forget to comment your doubts.